Hello. Hi, this is Vishal Kumar, and I'll be covering the section 1, the introduction part, and the section 2, pointing vector and radiated power. So, as of now, we are well aware about the multiple expansion technique, which we often use for electromagnetic and gravitational fields for larger distance. But as far as this project is concerned, we are trying to find an expression for the radiated power in the approximation order beyond the dipole approximations. And the interesting part is that we are trying to get the approximation beyond dipole approximation using the basic equations of electrodynamics and the techniques from vector and tensor calculus. And we are only using the fundamental relations from the classical electrodynamics and some mathematical transformations like Gaussian theorem, triple dot product, and etc. So the energy density in Gaussian unit can be written as W is equal to E k square plus B k square upon 8 pi. And when we take the partial derivative of energy density with respect to the time, so it can be written as 1 by 4 pi E dot del E by del T plus B dot del B by del T. And since we are considering the region, we are treating the region in the absence of any charge or any current, the Maxwell's equations can be written as del E by del T is equal to C curl of B, and where del B by del T is equal to minus C curl of E. When we substitute the equation 3 back into the equation 2, uh, it would reduce the partial derivative of energy density with respect to time is equal to minus C by 4 pi del dot E cross B. Here, we will substitute the E cross B value with by the by S, the Poynting vector. So S is the energy flux density, also the Poynting vector, and it can be written as C by 4 pi E cross B. And from this equation, from the equation 7, we can see that E cross B is equal to 4 pi S by C, and when we substitute back into the equation 5, we'll get the equation 6, which is del W by del T is equal to uh, minus C by 4 pi del dot S. Now, moving further, here we can see that the energy consumption from this expression, and when adding rearranging the previous equation, we can see that the energy conservation law for the electromagnetic field in the absence of energy, charges, and currents, this equation reduced to the equation number 8, that is del W by del T plus del dot S is equal to 0, that is the partial derivative of energy density with respect to time plus the sum of partial energy density with respect to the time and the divergence of Poynting vector, that is energy flux density, is equal to 0. Now we'll use the Gauss theorem on the LHS part and RHS part of the equation 8. But here in equation 8, the LHS would be del W by del T, and the RHS would be minus del by del dot S. Okay, so the LHS part would reduce to minus dw by del dt, which is equivalent to minus d by dt. Will taking the differential part out of the integral and integrated over of w over the whole space. And RHS part would become I is equal to mod of s arc square and over the complete solid angle d phi. Now here, since we are integrating the Poynting vector into arc square over the all solid angle, there is an interesting case which need to suffice. That is interesting thing that the field which contribute to the radiation has a dependence that is proportional to 1 by arc square, since we are only concerned about the farther distance. Let us explain it through an example. Let's say modulus of s is proportional to 1 by r to the power n, given that n is greater than 2, and we substitute back it in this equation, we'll find that the mod s into r square in case of n greater than 2, let's say n is equal to 4. So this would reduce to 1 by r square into d phi. Here, since r is tending to infinity, the entire expression integrand would tend to 0, which does not make sense, which is it is not contributing to the radiation. Now let's say modulus of s is proportional to r square or any r term. So then in that case, when substitute in this case, let's say modulus of s is proportional to n is equal to 3, where modulus of s is proportional to r to the power n given n is greater than 0. So in that case, it would become r to the power 5, and as r tending to infinity, it would tend to 0, which does not make sense. So the only field that is going to contribute to the radiation would must have a dependence of 1 by r square. Now, considering we'll expand the electric and magnetic field in the two order, that is zeroth order and the first order. Here E naught and B naught are proportional to arc 1 by arc square, since they are been written for electrostatic static charges, and E1 and B1 are for the first order correction. Hence E1 and B1 would be proportional to 1 by r. So and the expression for E1 and V1 can be seen through the Leonard Wickett potential, which we'll see in the later. See later. And here, the Leonard Wickett potential phi scalar potential field, and A, the vector potential field, can be written as the equation 12 and equation 13, where beta S is equal to Vs by C, and Ns is equal to R minus Rs upon R minus Rs, where Rs is the source, the vector for source charge, and R is any random vector. When we after calculation and substituting these equations and in the Maxwell equation, we'll find out that ERT expression comes out to be this, and BRT equation comes out to be this. Here in the previous in here for equation 16, we are assuming that E1 and B1 both are equal in magnitude and orthogonal. So let's consider how E1 and B1 are equal and orthogonal, equal in magnitude, and how it is orthogonal. So this part is proportional to arc square, which correspond to E naught, and this part is also corresponding to B naught square, since it is proportional to 1 by arc square, which we have covered previously. So let's consider this is the E1 part and this is the B1 part. So you can see here that mu naught and then 4 pi and 1 by 4 pi naught and C factor. This constant vector is equivalent, as we know, because of the relation between epsilon naught and mu naught. So we are not considering it here. We are only concerned about this expression and this expression. So Q and Ns are same here, and Ns minus Bs dot cross B dot S. And as you can see, if we are only concerned about the magnitude of E1 and B1, so the denominator part is equal, and here the denominator part is also equal in case of the E1 and B1. When we take the magnitude of this, so Ns would become 1. So this so in case of a when we take the modulus of this the numerator and the numerator here would be equal, as you can see from the expression itself, that the modulus of numerator and of E1 and the denominator and the numerator of B1 is exactly same when we take the magnitude of it. So here this proves that E1 and B1 have the same magnitude, and here you can also see that BRT, that is B naught plus B naught plus B1 is equal to the cross product of E1 E naught plus E naught plus E1. So which means that B is coming from the cross product of Ns cross E, which supplies that E and B are perpendicular. Hence E1 and B1 are perpendicular. So from the previous equation, we saw that E1 and B1 are both equal in magnitude and orthogonal. And coming to this part also, in case of S, when we put S is equal to E cross B, so when we do the cross product of E naught cross B naught, that would be proportional to 1 by R4. And in case of E naught into B1, it would be proportional to 1 by R ka cube. E1 into B naught would be proportional to 1 by R ka cube. From this equation 10, we know that the only dependence of 1 by R ka square is sufficient, is going to suffice. Hence, these all is going to be cancelled. Only E1 cross B1 terms is going to stay. So we are using that in the expression S, where C by 4 pi E1 cross B1, and we are using that the E1 and B1 both are equal in magnitude and orthogonal, and C by 4 pi is equal to B1 plus square, and we put that back into the equation. Uh, Here we put back that into the equation 9, which makes it equal to C by 4 pi B1 ka square R ka square into d phi. And now in the further section, we'll put BRT is equal to curl of A, where A is vector potential, and derive the radiated power. uh, okay, yeah, thank you.
Hello guys, my name is Athar Deshpande. So I hope you're enjoying the current YouTube electromagnetism series. My roll number is 210260012. Yeah, so welcome back. So currently we are seeing vector potential here. So introducing vector potential equation here. So our guiding light through the electromagnetism, but what is exactly the this entity and why it's so crucial to understand. So yeah, the vector potential denoted as A. of R comma T is a mathematical construct used to describe the electromagnetic field generated by electric charges. It's like a hidden language that reveals the patterns of electric and magnetic forces in the space. Yeah, looks fascinating. Yeah, perfect. So yeah, how do we go about calculating the vector potential here? Yeah, so we'll just break down the equation here. So yeah, let's dive into the heart of the matter here. So this is basically equation, yeah, ele- vector potential equation. At first glance, it may seem daunting, but not fear. We are here to unreveal the mysteries step by step. So yeah, this represents the vector potential in the Lorentz gauge, a specific gauge choice that simplifies our calculations. So it involves integrating the current density over the volume containing the charges, taking into account the distance between observation point and charge distribution is also taken into account. Yeah, so yeah, we simplify our equation here by this approximation of r dash is very less than r. So the Lorentz gauge ensures that our equation are consistent with the Maxwell's equations. Yeah, so adhering to the gauge equation, we maintain harmony between the theoretical framework and experimental observation. So these equations from 20 to 22 introduces some handy shortcuts to streamline the calculations. So yeah, we'll see the why we took this approximation. Yeah, so these equations allow us to approximate the distance between the observation point and the charges, making our computations more of a manageable kind by exploiting the symmetry of the system. So we can express this distance in terms of simpler variables, uh, the r dash and r. So we took approximation here. Yes, if this is the approximation, then this is exactly more often equal to 1 by r. Then then we introduce this unit vector here and write this. Yeah, so this is a system of charges located. This is our observation point, and this is our source charges spread across the volume V, and having each r dash as their coordinate. Yeah. So yeah, moving to the equation 23. This equation. So now we encounter the Taylor series expansion of the vector potential here. This expansion unlocks key total behavior of electromagnetic field. So basically, we'll go through the expansion. Yeah, Taylor's expansion allows us to express the vector potential as sum of terms, each contributing to our understanding of the electromagnetic field. So by dissecting the problem into smaller components, we'll get deeper knowledge of it. Yeah, so we define current density as here. Oh, it's can be written like this. Yeah, so this is the equation 25, which introduce the concept of the current density. What's current density's role here? Yeah, nice question. We'll see. Yeah, so basically J here, current density denoted as J, quantifies the flow of electric charges through space and time. It's like a it's like a river of electric current guiding the movement of charges and shaping the electromagnetic field around them. Yeah, nice explanation again. By so by understanding the current density, now we'll simplify the leading term over here. Yeah. So equation 26 simplifies the leading term of our vector potential expression. So it's direct connection to the time derivative of the dipole moment. We will see retarded time is dependent here. So basically, equation 26 is this basically is a relationship between the vector potential and dipole moment of the charge distribution. So by tracking the changes in the dipole moment over time, we gain valuable insights into electromagnetic field evolution. Yeah. So putting it all together, we see uh, this equation. We put our basically we solve this, and we get at least the leading order correction term. We get this, and yeah, So yeah, so indeed, the vector potential provides a powerful framework for understanding the complex interplay between electric charges and the electromagnetic field. So by this mathematical synthesis, we yeah unreveal the universe secret. Yeah, thank you.
Hello, so I am Gregor Goel and I will be continuing from here. So we have obtained the first term, the leading order term, the zeroth order term in this expansion, which comes out to be as deep dot by CR. This is taken at the retarget time K minus R by C. Now we look at the next order correction, which is first order in nth R prime. So the term is derivative of 1 by C square R integral over volume dv prime and dot r prime current at the retarget time. So we just substitute J as this term, which is summation over I ei vi of tau delta of r minus ra of tau. Tau is the retarget time again. So after making the substitution, we get this. So we get summation over I ei vi and dot r prime. And then we can simply write vi as dri by d tau. And then we can write this term as this. We basically get dri by d tau outside the summation. And then we'll have to add this term to make them equal. So we get 1 by 2 dri by d tau summation over I ei ri and dot r prime plus 1 by 2 summation over I ei and cross vi cross ri. Now let's look at the first term over here, which is this one. So since the vector, we want to find the magnetic field, which is the cross product of A with N. So if we add another arbitrary vector proportional to N to A, it won't change the field. So for convenience, we add this term 1 by 2 d by d tau summation of I, ei, and dot N r squared by 3. So we are adding this term to the first term over here for convenience. And then we can write the summation part as a contraction of the electric quarter-pole moment tensor with the unit vector n. So the electric quarter-pole moment tensor is this one, qjk equals summation of I, ei, xj of I, xk of I, minus ra squared by 3 delta jk. And we get this contraction, which is basically a projection in a sense of this tensor on n given d, the stylized d, equals summation over k, mu jk and k. So we can write this whole thing, this whole thing under summation, this summation I ei stuff as d. So we get half the value of d, the vector d. And then the next term is half summation over I ei and cross vi cross ri can be written as the cross product of M with the unit vector n, where M is 1 by 2c summation over I ei ra cross vi. And this both of these together give us the first order direction to A. So now we look at the last order correction. So we have this, we look at this now. So d square by d square 1 by 2c cube r integral over v dv prime and dot r prime square j. So over here, what we do is we just substitute the integral back 1 by c 1 by c integral over volume dv prime ji xk prime xl prime, and this will be the M, which is the third rank current quadrupole cancer. And we just subscribe it over here, and we get we get this last term correction as 1 by 2 c square r m double dot of r prime uh, unit target time nk nl ei. Ei is the unit target coordinate vector as usual. So now we have obtained all the corrections to A over here. So we have this first term, second term, and last term. We just substitute them in. So the first term is d dot of t minus r by c by cr. We just put it over here, d dot by cr. And the second term is m cross n. Sorry. Second term is d by dt of 1 by c square r m cross n plus d by dt of 1 by c square r d. So we add them over here and we get m dot cross n by cr plus 1 by 2 c square r d double dot. And the last term is over here 1 by 2 c square r m double dot n k n l l e i. And we just add it over here. And we just evaluate all these quantities at the retarget time tau equals k minus r by c. That's it for the vector potential. We'll next calculate p. Thank you.
So yeah, thank you Mrudul for covering this vector potential part. So now using this vector potential, we will try to find the magnetic field here. So let's do that. So we know that like how to find the magnetic field using the vector potential, we just have to take a curl of it. So that's what we are going to do. So here we took the curl of the vector potential which he had found. So we had the expression of the vector potential in the retarded time. That's why this t minus r by c explicitly written there to just like remind us that thing. So like it's quite straightforward thing. It's the identity which are going to use here. So it's like let's take any function f. So if we take that L cross f and f is a function of retarded time which is t minus rc, it also contains the term r and delta like del of that like a grade like it's the we are taking curl of that. So it also has that del by r del r terms and so so here we will use the kind of a chain rule we do that and we have done that in the class like we have done it explicitly in the class like how to prove that and all. So if you do that the final expression we get is that f dot 1 by c into the like curl with n is our vector the direction vector. So yeah, so when we do that here like del cross d double dot we'll get d double dot cross n. That's the same thing we'll follow and we'll get these four terms. Now what to do with these four terms? So let's look at this. So we name these four terms distinctly at bd bm b capital q b capital m. So they are respectively like related to electric dipole, magnetic dipole, electric quadrupole and current quadrupole term. So why? Because like this d m q and capital m were those things respectively which we have done in previous part which are covered by the students which who came behind before. So we can see that BD term, BM term, BQ term, and B capital M explicitly what they are, and we can see that how they what they're proportional to in terms of C. So BD is the most contributing term because it's only proportional to 1 by C square, where other terms are 1 by C cube, 1 by C cube, 1 by C raised to 4. Like because like C is the speed of light and which is that's the very last term. So that's why BD will come like contribute the most. So now we will calculate the magnitude of the Poynting vector in the following terms in those terms. So magnitude of Poynting vector is like c by 4 pi mod b square. So here mod b square we have four terms. We'll get like four square terms and we'll get the cross terms. So all of that. So last term will be of the order of 1 by c raised to 5. Here we can see that. And the other terms are will be of the order of c raised to minus 6. So now we have to look at these terms individually because let's say we want to calculate the intensity or something like that in terms of like we want to calculate the contribution of the to the radiated power. So we know that the electrical dipole term will contribute the most. So let's do that first. So it will be like p by 4 pi b d square r square d omega. D omega is the solid angle which is 4 pi. We know that. So as we saw previously that bd is d double dot cross n by by c cube I think. No, by c square r. ठीक है. So yeah, so we will do that. So here d double dot cross n mod square. So what is the best way to calculate this thing? So here what we do that we use a simple trick. Here we haven't specified what are our like direction cosines or directed like what are where are our z axis and all. So we have that freedom. So we say that d double dot is directed towards z axis and n is making theta angle with that. So that's why it will give us this term of like d double dot sine square theta d omega. And yeah, so we get this term and let's integrate that now. So I think one mistake is we have done I have done here with like d omega is sine theta d theta d phi. I just missed the sign is here. Here should be sine cube theta should be here. So apart from that, yeah, everything is there. So yeah, it should be 2 d double dot square 3 c cube. So it's proportional to 1 by c cube. So this is the leading order uh, contribution to the radiated power. So let's calculate now the next order, which is the magnetic dipole contribution. So again, there were like mod bm square and mod bm was m cross n. So again, we will use exactly the same things which we had used now, where like direction cosines and all, and we'll get the 2 m double dot by 3 c cube. But here we can see that the contribution is 1 by c power of 1 by c raised to 5. Why? Because m, like as we saw in the Mrudul slide or somebody else's slide there, like they had shown the expression of m beforehand only. So I'll just show you that. So here we can see that the below equation 20 m is equal to 1 by 2c and whatever it is that calculations are there. So it is in the power of 1 by c. So that's why it is in the power of 1 by c raised to 5, the contribution of that. Okay, so while moving forward, so now we have BD and BM contribution. So let's do the cross contribution there. So BD dot BM. So we had BD as D double dot cross N and BM as M double dot cross N cross N. So here again, this is mostly mathematics where A cross B cross C, where we'll use the BAC CAB rule and we'll get this expression of like N into N dot M double dot minus M double dot. And now we will distribute this D double dot cross N over all of this space. And we know that d double dot cross n dot n should equal to 0, like a dot a cross b is 0. So the first term will contribute 0 and the second term will be d double dot cross n dot m double dot, and there is a minus sign. And also this is a vector triple product, and here we use that thing that we can flip between the cross and dot terms and just change the sign. So it's the whole contribution is n dot d double dot cross m double dot. So now looking at this thing, we can again use the same thing that like one of those things are directed towards the z-axis and angle is theta. So it will give us like something like d double dot cross m mod cos theta. And in the d omega, we will have sine theta. So it will be sine theta cos theta. So like proportional to sine to theta. And integral from 0 to pi, it will give us 0. So this term will contribute 0. Okay, so we can do exactly like not exactly but kind of a similar calculations in bd dot bq. So we know that bd is proportional to d double dot cross n, and now we know that bq is proportional to d triple dot like capital D triple dot cross n, which is where the capital D is a quadruple term. Huh. Capital D is proportional to quadruple. It's not exactly a quadruple term. It is like the projection of the quadruple term on the vector. Like we can see that here. 1 minute. Yeah, we can see that here. The yeah, so the sum or I is the contraction of the quadruple moment tensor with the unit vector n yielding some vector d. So like contraction of that with the unit vector. So it is q j k n k. It's like that, like multiplying a matrix with a vector q. So yeah, let's look at it again now. So now bd dot bq, so we will have that. So now again we will again distribute this cross product over this dot product, and we'll get this like d double dot dot n cross, yeah, all those things. And from that we'll get the two term d double dot cross d capital D double triple dot and the next term. And now we will look at the indices specifically. Let's look at the ith indice. So d double dot will give us di and d capital I, and d capital I you can write it as a vector notation like indice notation as qij nj, because and here summation is implied. We are using that Einstein summation where the summation is implied over the coordinates. Okay, so and the term below that which is n dot d double dot, which that will give us di ni, and again n dot d triple dot, it will give us uh, it will give us nk dk, and that in turn will give us nk qjk nj, like the similar things which we have done above. So now how will we calculate this thing? So let's again look at these terms. Let's look at the equation number 36. Here we have nj. So it's like integrating any one, like nx, ny, or nz over d omega. Like if you just look at it, nx is nx is sine theta cos phi. If you integrate it over the d omega, it will give us zero. Like we can prove that by taking each and every term that it will give us zero nx. Like it's very easy to see. Like in case of nx, it will be like sine theta cos phi, and again there will be a sine theta in the this thing d omega, but there will be cos phi, and we'll integrate that cos phi from 0 to 2 pi. It will give us 0. In ny, again, there will be a sin phi, will get 0. And in nz, it will be sin theta cos theta. So it will sin 2 theta, and again, it will get 0. So that's what happened with the individual term. So this equation 36 will go to 0 when we will integrate over the d omega. So now let's look at equation 37. So here we have three different Ni, Nj, and Nk. So now how to do this? So the thing is ki if you do this cumbersome calculations for all 27 things, we tried it using the code also. So you will get zero each and every time. But there is more to it. So like as I told you, right, it's very easy to integrate the Ni component over the complete solid angle gives zero. So but same goes for triple product. So the thing is, whenever there are the odd number of contributions, it will give us zero. So the theory is that the product of an odd number of Ni factors is an odd rank symmetric tensor. We know that we can see that it's an odd rank tensor because Ni and J and K will be rank will be odd, and it's a symmetric tensor because even if you swap the stuff, the multiplications won't change. So symmetric tensor, and the only tensor, so and this tensor is invariant under the axis rotation, and that's why, and the only tensor which is invariant under axis rotation is zero. So that's the theory of it, and the thing is ki Apuro is going to cover more of it. So the thing which you have to remember right now is just that whenever there are odd multiples of n, we will get zero, and that's what happens with case of bm dot b capital M and bq dot b capital M. So let's look at it like how that happens. So and there are like we see that there are like five instances where ni is uh like ni occurs five times in each and everything. So let's look at our expressions above here again. So let's look at that. So let's say bm dot b capital M. So we had n cross m cross n, so two n terms here, and capital M had one, two, three terms. So we'll have total five terms. So it will go to zero. And again, let's look at bq dot b capital M. Here we had d double dot, but we know that d double dot in turn has his own n. So we'll again have two terms here and three here. So multiplication we have five terms. So that's what happened in general here. So okay. So we are done with this. So now let's look at the remaining term. So let's consider the product of bm dot b capital Q. So let's do that. So bm we know that is n cross m double dot cross n and dot d triple dot cross n. So here again we will so here again we will use the same thing, like we will do the BAC ABC rule, then we will distribute, then we will take the dot product, and in the end we will get this, like we will exactly the same thing which we done here above in the case of bd.bm, because we had exactly similar expressions there where we had capital D in like instead of d small d. So that is the same thing. So we'll get n d triple dot cross m double dot. Again we'll use the index notation where d double dot cross m double dot, it will be epsilon ijk dj mk double dot, like we have done this extensively in our class also. And n dot, like dot where, so like we are looking at the only ith component, so it will be ni, and that, so again the summation is implied here. So if we rearrange the stuff again, we can write this dj as qjl nl, write that, and we'll get this expression. So now here we can't use that trick because here n comes two times only. So the integral we have to take of two unit vectors over the solid angle. So again the Apurva will go like will tell us more about this integral, like how it happens and all. But here let's let's do the quick revision. Like we can actually do this thing. It's very easy. So let's take a example. Let's take a nx and y. So nx and y, what will give us? What it will give us? It will give us sine square theta cos phi sine phi, and we have one sine theta from d omega. So it is sine cube theta cos phi sine phi, and cos phi sine phi again it will give us sine 2 phi integral from 0 to 2 pi, it will give 0. That's how it happens in cross terms. And let's take, if you want to take check any like not so like same terms, it will be, let's take a z term. So it will be cos theta. So cos square theta, and if you integrate cos square theta, it will give us 4 pi by 3. And this happens every time. So yeah, so that's not exactly a issue. So that's why it will be 4 pi by 3 del JL. There are only 9 terms you can calculate also. So again, we can note that Bm dot Bq is now, let's substitute that Ni NL part here. So you'll get epsilon ijk q triple dot JL delta JL Mk. And now let's contract like delta JL. Let's replace all L's with J. And so now we'll get epsilon ijk q triple dot Ji Mk double dot. So now let's observe one thing. If you know that epsilon ijk is the Levi-Civita symbol and it is the antisymmetric axis. What does it mean antisymmetric? If I flip to like I to j, I'll get the minus of epsilon ijk. That's what antisymmetric tensor means. And we know that the capital QJI, which is a quadruple electric quadruple moment, it is a symmetric tensor. So let's do one like um one mathematics here, like point of mathematics here. So let's invert j and I. So what will happen? Epsilon jik q ji mk, and this q triple dot ji is qij, like sorry, I messed up. Qji is qij, but epsilon jik will give us minus epsilon ijk. So it is like this term and its minus are same, so we mean, so it is zero. So bm dot bq also give us 0. So yeah, so we saw the terms which will contribute, and the other terms which how they going to give us 0. We did that part. Now Apur will cover more about the electric quadrupole radiation. Over to you, Apur.
Hello, I'm Apurva, and I believe in the last part, Atharv explained the contributions from the electric and magnetic dipole moments and the terms that were not contributing anything. In this part, I'll be talking about the electric quadrupole moment part, and the anapole radiation part. So now let's look at the electric quadrupole radiation part. So it comes from this term, mod BQ square, which is just script D triple derivatives with respect to time cross n mod square. So now this first expression, this can be easily evaluated. This is called the Cauchy Binet Cauchy identity. So it can be easily evaluated as like this is just a cross product dot cross product. So this is like a vector dot uh, cross product of two vectors, which is a scalar product, which has a property of cyclic permutations. So it can be easily permuted. Then we get a term with a cross term like a cross b cross c, which can be written as a dot c into b minus a dot b c. And if we write it that way and use the knowledge that n is a unit vector, we can get this expression easily. Let's look at it in the index notation form. That would be much more easier, writing this in index notation form. Now our script d is just the resolution of the q, that is the electric quadrupole moment along the unit vector directions. So this, so di would be just qij nj, and if you substitute everything, we get this expression. Thus the power for the electric quadrupole radiation would be just this factor times integral over all integral over the surface, the angular integral over the space time, which evaluates to be this. Now to evaluate this, we use the following identities, which are given in Jackson's book. Let's try to prove this, at least get an intuitive idea how we get this. So Qij and Qik, this depend only on the tau, that is the retarded time. So the integral over d omega won't affect that. So we have just integral ni and j d omega. Now ni and j is together is like a symmetric rank 2 isotropic tensor. By isotropic, I mean if we it does not component of that tensor does not depend on the coordinate system that we choose. And an isotropic tensor can be written in terms of the canonical deltas. So for two indices, the only possible canonical delta is delta ij, and let's say some so this integral would be delta ij times, let's say, some constant a. Now to find this constant, we can just substitute ni and j, and we can put ni equals j equals to I, so we'll get ni, which is ni square, which would be 1 by 3 unit vector, and d omega would give you 4 pi. And we can also find it by just choosing I as x and j as y. So nx into ny would be just sine theta cos phi times. So sorry, we can choose ni as x and nj as nx, both as x. So it would be nx square. That would be sine theta cos phi whole square times sine theta d phi d sine theta d theta d omega d phi. Sorry, and evaluated the integral, we can just easily get this vector. And using the similar similar analogy, we can go for the four indice term as well. So the possible Dirac delta combinations are this. So let's say A times this plus B times this, C times this. Similarly, contracting any two of these indices, or just choosing uh, any specific coordinate system, we can find the constants and we get them to be 4 pi by 15 for all. There's one thing about these products. If these are for the even number of terms, if the number of unit vectors in the product are odd, the overall integral vanishes. We can see that in the sense that we can't really form any uh, we can't really form any tensor of rank of any odd number rank from Dirac deltas, because if we contract, if it's symmetric, we can flip any two of these indices, and because Dirac delta is only two, we make like pairs of 2 2 2, and because of this there would be one index that would not pair with anyone, and that would result in an anomaly and that will vanish out. So thing is, we can't really form a symmetric isotropic tensor of odd rank from Dirac deltas. So using that property, we can just look at we can just prove that if it's an odd number of unit vectors, it vanishes. We can also check it by choosing one of the terms, like for 3 nx ny we get 27 terms and we can evaluate it easily, but for higher order terms we need to generalize it. So using the identity and substitute it upstairs, here we get ni nj term to be delta ij, so we get qij qia. For the fourth order term, if we substitute it from here, uh, the first term would give me qik, which could be qij. The second term would give me qii and qjj, but our quadruple moment tensor is traceless, so that term vanishes. From here we get qil, qil, qk, qik and qki, so which is just what we need. Uh, we can just those are all just dummy indices, so we can just write it as qij, and evaluating this entire expression, we can get it in this form with this vector. Uh, so this was the contribution from the electric quadruple moment. If we look at the NPOR radiation part, we have this term 2bd dot b script m. Substituting form of bd and form of bm into this, we get this expression. Now again we have this term which has two indices and product of two unit vectors and product of four unit vectors. This we got from contracting the Levi-Civita tensor, because two of the indices are same here, so we can contract easily. We get delta pi delta qr minus delta pr delta qi, and substituting it we can get this expression. Uh, so now power radiated from this term, that is ia, would be just this thing, and integrating over d omega for this nk ni and this thing, this four combinations would give me this term. I can write this term in the form of some other other vector, that would be t. The t here, it's called the anapole moment or toroidicity, where t tau is defined in this way. This is just this writing in the form of j, the form of m earlier, and this is called the toroidicity. So this was the contribution that we got from the anapole radiation part. So now let's sum everything what we did earlier. So we looked at the radiated power up to 1 by c power 5 contribution, c power 5 order. So we had these four terms where id gave us this contribution of 1 by c cube, and the other three gave us this part. The second and fourth term are also proportional to c power 5, because in this term the m has an instance of 1 by c in it in its definition. So that would give me 1 by c power 5, and t here also has an instance of 1 by c. So that would also give me c power 5 term. So these are proportional to c power 7. Any consequent terms would yield higher order of order 1 by c power 7 and higher. Notice there won't be any no term of 1 by c power 6 or 1 by c power 8, because those are even number terms, and those terms vanish the similar way that we saw in the case of the 1 by c power 4 term. So in the integral what we get is we get uh, the unit vectors odd number of times, and integrating it over all integrating it over d omega just vanishes. So there won't be any even power contributions, just odd power contributions. And generally we neglect the anapole term, that is this last part. uh, we neglect it because just considering the electric dipole radiation is just it's a sufficient approximation, and we only need to consider it if uh, only need to calculate, it's like a correction, we need to calculate only if id is equal to 0. But now there's a subtlety, because if id is 0, which means d is 0, d double dot would be 0, and if d double dot is 0, the ia, that is the coming from the anapole part, that would also vanish. So we don't generally need to calculate the anapole radiation, that's why it's neglected. But if we need to look at higher order corrections of the part of the d part of the electric dipole part, we need to consider the toroidal part as well. uh, and why the reason it's called toroidicity is or for made analogous to a torus is because in static case the electromagnetic field of a torus is zero outside the system, but for time dependent sources it's defined using this quantity, which is the toroidicity or toroidal dipole or anapole moment. Okay, so this is like a dipole moment from because of a torus, frankly speaking. So using the similar analysis that we did in section 4.4, that is the one where we found the intensity from the electric dipole part. So this is just analogous to that, just substituting d as t, and we can find the intensity from the toroidal part, which would here again t has instances of 1 by c, so this would be proportional to 1 by c power 7, which would be even lower order. So that's why we don't consider it. But if we include it into the electric dipole part, this just completes the square, and we get this simpler expression. So this can be seen as toroidicity is just a correction to the dipole moment in this way. So now in the summary, in the entire project, what we did is we expressed the power of the electromagnetic radiation in the approximation beyond the dipole approximation, that is with terms proportional to 1 by c power 5, and I think which is a accuracy significant for comparison with most present day measurements. Okay, so thank you.